of this type 2 curve C in P. How many have I got? 1, 1. So this total set of equations has several nice properties. And so I'm going to talk about, first I'm going to talk about the nice property 2. So this is to do with deforming the equations inside the same format. Right. So the point to notice is that the point I want to make is here. I've got this x1, x2, and I've got this x2, x3 squared y, z1, z2, and you know the rolling factors. So when I'm doing z1 squared goes to z1, z2 goes to z2 squared. Right? So if I'm changing first equation, second equation, third equation, involves these terms, right? But don't involve the second column. Right, so if I do x1, x2, and then x2 primed, and then x3, and then I'm going to just replace this x3 cubed by y2, y, z1, z2, right? So I've replaced x3 squared by y2. Okay, so I have a different number of variables now. I have two new variables. There's this x2 primed and the new y2. Right, but I can still do the same transformation. I can still do the same rolling factor manipulation here. So I can still write down wedge 2 of m equals 0. So this is now m. Let me write this m primed. And three other equations. So I want to. It's useful to write these equations in a. You know, I mean, I can just write the three equations if I want to, but I could also write. I can also write them as. So you know, if you think about what's happening here, there's x1 squared here. That's quadratic in this, and then I'm replacing him by the thing which is bilinear in these, and then the thing which is quadratic in there. So I can really think of this as saying that z1 squared is. I can really think of the top line as I've got a quadratic form, a bilinear form in the two rows of the matrix. Right, and I'm setting that quadratic form evaluated on Z1 to be 0, and then the same with the bilinear form now Z1, Z2. So let me write this as how do I want to do it? M primed x1, x2 primed, y2, z1, x2, x3, y, z2. So I want to see z1 squared. So I'm just going to treat the two equations as if they were quadratic form evaluated on the two lines. Right? Right, and so, you know, what's this matrix? I'm writing down the matrix of quadratic form. So I've written down the z here, saying in the first term I want z1 times z1, so z1 squared. So if I've got that, then I want minus a and then minus, what's the term here? Plus b. And I think I've got 0 there. Is that right? So the thing I'm writing down here is a quadratic form in the two rows here. So when I do it the first time, I'm taking the top row of the matrix, and I'm saying, right, I'm going to take z1 squared, and then I'm going to take, of these terms, I'm going to take x1 squared times a, and then of this term, I'm going to take this squared times b. I think I've got this right. So when you do this, this is a little 2 by 2 matrix, 2 by 2 symmetric matrix. Right, so I've got 9 equations. 9 equations. And you can check that there are 16 syzygies. Between them, that are consequences of the format. Okay, so this is the thing. This is the point I'm insisting on. So you know, what do I mean by syzygies? So I've got this matrix M. So let's just think of M as being M11, M12, M13, M14, M21, M22, M23, M24. Wedge 2 there. So this is 6 equations. So whenever you have equations in a determinantal form, then they carry some syzygies with them. Because I can take this matrix here. I can write, for example, suppose I do this, M11, M12, M13, M14. Right? So this is now a 3 by 4 matrix. And suppose I choose 3 columns. So, for example, choose the first 3 columns. Right? What's the determinant of this matrix? It's identically 0. It's not just 0, it's identically 0. Right? At the same time, so this is saying M11 times the minor M12, M13, M12, M23 minus M13, M22, and then plus M12 minus M12 times similar plus M3 is identically 0. Yeah? So I'm writing down 6 equations, and this trick gives 8 syzygies. Okay, it gives 8 syzygies because there are 2 different rows here, and I can repeat the 2 rows, and each time I do it I can choose 3 of the 4 rows in 4 different ways.
Are they independent?
They're different syzygies. Now, of course, they're not independent, and they don't generate a free module. You know, there's a so look, P0, P1, P2, P3, P4. The end. Right? This is mapping down to R. This is A. This is just a polynomial ring. So this is K of x1, suffix n. Right? There are 9 here, there's 16 here, 16 here, 9 here. And the, you know, there's a sense in... So, you know, these are sort of basically symmetry. So there's a P2 has a quadratic form on it, and P3. So this set of matrix and this set of... Anyway, let me not go into it. I'm writing down 16. I'm writing down 8 syzygies here, right? And you know, so they involve that they're different as written, at least, right? Because they involve different terms. Yes. Right? They're not certainly not. There are certainly 16 second-order syzygies that hold between the syzygies. Okay, so where do I get other syzygies from? Well, you know, these two. When you think about this matrix, how do I? There are 8 others from the M primed A M transpose equals 0. And how are these obtained? It's basically some similar matrix trick. I think by good luck I didn't bring the paper with me, so. So look, I'm going to. There is just a little matrix trick, and it looks like this. I don't. So I'm writing down 8 other syzygies. Let me just do it. Right. So I have 0, 1, minus 1, 0. I call this n. Right. If I write T A N A T M N transpose of M cis. Okay, so I'm taking this matrix and I'm making a quadratic form which is pulling out one of these. I mean, this is a 4 by 4 skew matrix with entries, the 2 by 2 minus of M primed. So you know, I mean, this is complete trivial. If I take this matrix and I multiply it by, what am I saying? I was right first time, transpose there. If I take this matrix and I transpose it so it is sideways, then it's a 2 by something matrix and I can multiply here. I multiply that out, I get a row of 4. I multiply that out by this row of 4, I get a 4 by 4 skew-symmetric matrix, and the entries of that are 2 by 2 minus of the M prime. Right? And then at the same time I can do something like, so the entries here are, these 2 by 2 minus are some of the relations, right? And now I can mix these relations with these relations, right? Because these are also obtained by multiplying the matrix, right? So imagine that I take this and multiply by this, right? Then I get something which is identically 0. On the other hand, I get something which can be written out as a combination of these matrices and these matrices. Okay. So look, I've got the argument written down here. It's just, I'll get it wrong if I. There's a trivial argument based on the matrices. So based on the fact that it's based on the fact that the three equations I obtained in this way depend on the two rows here, according to this rolling factors, right? And therefore, if I have the relation obtained from one row or the relation obtained by transposing that from the other, then the difference between the two relations is just a combination of 2 by 2 minus here. So I'm sorry, I'm making slightly heavy weather of this, but so I'm getting 8 syzygies plus 8 syzygies. Right? And the point is, the point is not exactly what the exact form of these syzygies are. We don't really care. Right? But the point is this, that the syzygies that hold between these 16 relations, so I write down 9 relations, the 16 syzygies, and the 16 syzygies are just a consequence of the way I've chosen these equations. Therefore, if I change the m primed, and I change this matrix here to anything I like, I get a flat deformation. So, to be concrete, so given C with the equations that I had, x1, x2, x2, x3, x3 squared, y, z1, z2, and z1 squared, z1, z2, z2 squared equals the thing I had, the thing that's still there. Etc. I can change, I can introduce x naught in degree 0 and do x1, x2 plus lambda x naught. Let me just write plus x naught here. x2, x3, and then I can do x3 squared, and then I can do plus some multiple of x naught here, if I want, x naught times linear y, z1, z2. Right, and change as appropriate. Right, and the only important thing here is that this matrix has these special coincidences. Right, and by doing this, the matrix no longer has this first coincidence. So in particular, now, the equation of degree 2 can go from rank 3 to rank 4. Right, and so by doing this, I get by doing this for different choices here. So I can also change the A and the B. Right, I can take my surface curve C out into a surface S of type 2. I can do it into 2B to do it first. So this means so maybe I'll better put a lambda in there after all. i.e. S has a base point, Ks has a base point, and the canonical image phi S to this quadric in P3 has image quadric of rank 3, that has quadric of rank 3 if lambda is 0. Okay, so, and we get all the surfaces, we get all the Horikawa surfaces in family 2b in this way. I have just rubbed out the equations. I'm going to have to write them out again. Right, or I can do lambda equals 0 and change to lambda not equal to 0, and this gives surfaces in type 2a, where Q is rank 4. Right, so you know, most of the argument here is taking place on the level of the curve. I do the curve, I understand the ring over the curve, and then I say we're going to work within this format. Right? So if I start off from the surface S, I take the general curve there, I do some calculations on the general curve, and then I say, well, the surface S is certainly some kind of deformation of the curve, some kind of extension of the curve in degree, with an extension parameter of degree -1, of degree 1 here. And so I get every surface by this. This isn't just a construction of a particular surface. Every surface of type 2b arises in this way. And they all arise with 0 there, and if I change the 0 to be non-zero, then they move out. And so, I'm getting this part of the Horikawa picture. So this is 2b. It has some dimension. I think it's 39 dimensional or something, but I'm not especially concerned with the dimension, and here is 2a. So there's a moduli space, or a parameter space, of surfaces of type 2b, and they're given by these coefficients and then modulo some relations that I'm not prepared to discuss, that I don't understand, that I don't want to discuss. Right? So this is given locally by lambda equals 0, or x2 prime equals x2. Okay, so basically there's nothing very surprising here. If you've got a quadric of rank 2 of rank 3, then you expect to be able to take it out to a quadric of rank 4. And I think you could do this by arguing directly on the ramification locus. Okay, so now I want to explain how to get how to do the the part 1, deforming outside the format. Right, so x1, x2, x2, x3, y, x3 squared, y, z1, z2, and then these equations, z1 squared, x1 squared, a minus x3 to the 4th bit. So, you probably noticed that I'm very fond of writing out Pfaffians. I hope I've just... So I'm going to write six by six matrix, skew matrix. Right, so again, I'm only writing the superdiagonal elements. 0, x3 squared, x1, x2, x2, x3, z1, z2, z1, z2, a, 0, x3 squared, b, y times b. So what have I done? So this is extra symmetric. So it's a skew matrix, and it's of the form. So let me write B, A, B. Okay, maybe this isn't so good. It's of the form M. Let me write N, M, M, N, minus M, N. Right, and so actually there's this one. This guy's got multiplied by a little factor there. Right, where N is skew and M is symmetric. Right, so let's pretend the B is not there just for the moment. Right, if B is not there, then M plus N is an arbitrary 3 by 3 matrix. Right, so I've taken an arbitrary 3 by 3 matrix and I've written him as a sum of a symmetric piece and a skew symmetric piece. Right, if I've got a 3 by 3 matrix, I can take M plus M transpose and M minus N transpose, and okay, so this guy here is symmetric, and there's a little block here. There's a little 3 by 3 block. 3 by 3 skew symmetric matrix only has these 3 entries, and then it's this block is repeated twice. So, it's useful to think about how many independent entries this format has. So it's a skew symmetric. It's the upper triangular elements here. There are 5 plus 4 plus 3 plus 2 plus 1. There are 15 elements there. But I have commanded 6 coincidences. I've commanded that this matrix is symmetric, and so that's 3 coincidences. And I've also commanded that this one here is a multiple of this, so that's also 3. So this format here, this has only, so not 15, but only 9 independent entries. Yes? And now you can also calculate the 4 by 4 Pfaffians. Right? Now, how many 4 by 4 Pfaffians are there? So the Pfaffians are in one-to-one correspondence with these entries, right? Because if I take this entry 1, 2, then I delete row 1 and row 2. I'm left with rows 3, 4, 5, 6, and 3, 4, 5, 6 is a Pfaffian. Yes? And so it turns out that there are of the Pfaffians, 9 are independent, and 6 others are equal to simple multiples of them. Okay, so I'm saying this is a kind of magic. This is a cookery for writing down 9 equations where there are going to be lots and lots of Pfaffian syzygies holding between them. Right? So I say, for example, if you calculate, if we go down into this corner and I calculate this Pfaffian, I'm seeing z1 times yb minus z2 times x3 squared b, and then plus 0. Right? And so what did I say? z1 times yb. So there's also z1 times y there, and x3 squared times x2. x3 squared, the one I was referring to is this one times this minus this times this. Yes? And so what I'm seeing is that the Pfaffian obtained down here is just equal to the Pfaffian up there, in this case multiplied by b. Right? So although there are 15 Pfaffians there, if you calculate them, you'll discover that there are 9 and then 6 repetitions. So there's a little trick here, which is what's happening here is, I'm saying it in terms of magic, but there's a geometric interpretation. Right. If I take a 3 by 3 matrix, let me say, I don't want to use the same letters. Let me say G. Right. Then wedge 2 of G equals 0. So let's say with generic entries. Then wedge 2 of G equals 0, all 2 by 2 minors of G equals 0, defines the Segre embedding P2 cross P2 embedded into P wherever it goes, 8. Yes? On the other hand, if I take G and I write G as symmetric plus skew, so M is symmetric and N is skew, then the 4 by 4 Pfaffians of N, M minus N, N, this is now a skew symmetric matrix, right? And it's got 9 skew by skew. These generate the same ideal. Right. So this one here defines. This one is the conventional and easy thing that everybody knows from their first year of algebraic geometry. This is a sort of basically, curious and perverse way of writing the same information. So you have to do a little calculation to check this. It's very easy in computer algebra. If you do it by hand, it'll take you an hour or two. Right. So another way of saying this is here is P2 cross P2, and I say it is a non-generic linear section of Grassmannian 2,6. Right. So I've got, if I think of V1 and V2 here, so V1 plus V2 is so this is three-dimensional vector spaces. Then P2 cross P2 is I choose one point from here and one point from here. Right. Grassmannian 2,6 is I choose a two-dimensional subspace there. But if I'm going to take a two-dimensional subspace here and I insist that one point is in there and one point is in there, then I'm getting P2 cross P2 viewed as a subvariety of Grassmannian 2,6. Right? And this is how you write that in equations. Okay? In any case, you know, the 9 Pfaffians, these are 4x4 Pfaffians of this 6x6 guy. Have 16 syzygies. And they're really the obtained from the you know, the basically Kramer's rule. Right. So so I told you if I've got if I have a 5x5 guy, I can calculate his Pfaffians, and each of the rows of the matrix provides an identity holding between those relations. So if I do that, then I get 16 of them, and those are the that's the 16 syzygies holding between them. Okay, and this means that, so the corollary of this, this format provides the 9 Pfaffian equations with 16 syzygies. So automatically, I mean, it also provides so automatically. It's not grammatical, but I'm going to stop the sentence there. You understand what I mean? So in other words, suppose that I'm going to write down 9 equations, and they're obtained as the Pfaffians of the 4x4 Pfaffians of this. Then just by virtue of the structure of this matrix, there will be 16 syzygies holding. Right? And so the consequence of this, exactly as before, is that the format guarantees the syzygies. Right? And so therefore I can vary the entries of the 6x6. I should have given him a name. What's a good name for this one? I don't know. M6. Subject to the same extrasymmetric, and get flat deformation of my ring. Okay, and that's what. So you know, what do I want to do with this matrix? Well, first of all, these are the equations of a curve, and so I want to take the curve and make it into a surface. So you know, so I'm going to choose an x naught. So remember when I did the x naught before, the thing I was allowed to do was to change this entry here. X2 goes to x2 plus x naught. So I was allowed to think of this entry as a new variable. Right? And that was the thing that allowed me to take the quadric of rank 3 and make it into a quadric of rank 4. Right? So here I say I'm going to work within the limitation that this must be kept symmetric. Otherwise I don't know how to deform the equations. But I can still mess around with this. I can make this plus anything. So, you know, plus x naught times L. Right? And so, you know, and I'm not restricted as to what the B can be. I can change this a plus x naught, a prime. Right? And by doing this, I can take, so I can take these equations that define a curve and just put in one more variable and just generic functions of this variable and still get a surface. So I can take surface, I can take curve C and extend to a surface S, so that C is given by x naught equals 0. Slightly more systematically, I could think of the A and B, I can think of all the entries in the matrix as being generic, as just being, so I can think of this as being some polynomial, and this as being the B and, and so on, the A as being some polynomials. So I'm already using up most of the entries here. There isn't so much freedom. Right, and so, I mean, it's a fact that S is a S can be chosen a non-singular surface. Right. On the other hand, I can also take the curve C and just deform it to a new curve C lambda by putting here lambda. So I'm going to change this entry. This entry is of degree 0, and so I'm going to change them to lambda times a constant. So put lambda in this matrix, whatever it's called, M6, 1, 2, and lambda B in M6 of is it 4, 5? 4, 5. Okay, so now this is very good. This guy lambda means that, whereas before I had this equation x1y x2 cubed, x2 x3 cubed, now I have the equation lambda times z1 equals this. So that equation just removes z1. Z1 is no longer needed as a generator of my ring. Right? And slightly more subtle point is that this B is of degree 2. So I can think of the B as being, for example, y plus other stuff. Right? So this lambda deformation is exactly the thing that allows the curve to move away from the hyperelliptic locus. So when I do lambda not equal to 0, right, then the Pfaffian 1, 2, 3, 4, Pfaffian 1, 2, 3, 5 is lambda z1 equals something. Right? And, the lambda 1, 2, 4, 5 is lambda times lambda squared B equals something. And B can involve y. So then this looks like lambda squared y equals some other terms. Right? So these three equations eliminate Z1, Z2, and Y as generators of the ring. So, I've been talking about this curve as if it were a kind of only exists on the surface. But, you might be interested in the curve also. So C is a curve of genus 6. and I've got on it this P plus 2G12 in the half canonical of C. And then what I want is that C moves out to C lambda, and C lambda is C5 in P2. Right? So this is sort of, in some ways, sort of quite bizarre. I've got this curve which is a double cover of a conic with one marked point, and then the other 13 others there. This is a plane curve. And then this is a plane curve of degree 4. It's supposed to deform out to a curve of degree 5. Well, of course, that's not a deformation. It's not a deformation as written. Something more subtle is happening. So you know, the picture here is not a suitable ambient space for this curve with this ring. So instead, I'm saying I take C contained in this P 1, 1, 1, 2, 3, 3. So there's a Y, Z1, Z2, given by 4 by 4 Pfaffians of M6. Right? And so, you know, there I really have, this is a variety embedded by this half canonical ring, half canonical divisor. And so it's a canonical, it's a Gorenstein ring. And then I say, and I now allow you to change some of the equations a little. So as soon as that lambda is non-zero, then Y, Z1, Z2 are combinations of, you know, x1, x1, x2, x3, and the only remaining relation is a quintic. So there's a sort of F5. I'm not quite sure where I get, I haven't thought about where this comes from, but so somewhere in here, after substituting out for Z1 and Z2, I've got a relation involving, which is of degree 5 and which is not covered by the other, which is not covered by ZG from the other equations. So I don't really know how to explain this, but so you know, there's a geometric thing that's happening, which is where inside the moduli space of curves of genus 6, I have this curve which has this non-generic property. It's got a G1. It's hyperelliptic. So I take its hyperelliptic together with that half canonical class. If I vary the curve C, the set of its half canonical classes also moves around. I can certainly find a small deformation of the divisor, and so if I move away from the hyperelliptic locus, then I have to do all this strange algebra if I want to see it in algebra. Okay, and then you know, to complete the picture, I can do both of these things. I can move this out. I can move out the curve out to a surface, whilst keeping it hyperelliptic. Having done that, I can then put in the lambda not zero, so I get out this these are the Horikawa the non-singular quintics, the non-degenerate quintics, the quintics that have no base point that map to ordinary quintics of space, and somewhere in the boundary, of their component, there is this these guys of type 2b. Okay. So anyway, I'm describing the result rather than how, all the calculations you need to back this up. So so if you go to the if you go to the way the original if you go to the way the equations are written, right, then you know it turns out that if I want to, I can, so you know, the upshot here is I can add plus deformation parameter, you know, call it whatever you like, delta times x naught here, or I can add lambda here, which means that, you know, z1 is this, or better still, lambda squared y squared, sorry, lambda squared y is x1, x3 minus x2 squared. Right? So I can either have this lambda or I can have this delta. And if you study the deformation theory in more detail, you'll find that lambda times delta equals 0 in the Kurenishi space, in the space of deformations. So I'm not going to argue about that because it's a hard calculation and you have to do much more deformation theory to be able to do it. So you know this picture here. This picture here is saying, you know, this is lambda not equal to 0, and this is delta not equal to 0. And this equation is saying that delta times lambda equals 0. Okay. Let me say just a couple of words more about this Horikawa-Dix case. So PG equals 3, P squared equals 4, and 2 base points. So again, I'm going to take the general curve C in Ks. Right. So again, you know, this is Horikawa. And then my student Duncan Dix, around 1985. You know, Reid did this in algebra. In really quite complicated algebra, it's basically impossible to read, right? And so the assumption is that Ks restricted to C is P1 plus P2, and then plus a G12. Okay, so we have to go back to the beginning of the argument. We have to go back to the beginning of the argument that because there's a G12 there, this implies that C is hyperelliptic, right? And the genus of C is 5. That's exactly as before. And so its genus is 5. This means it has 12 branch points, and they are P1 plus P2 and 10 others. So, you know, there's nothing very difficult about the graded ring corresponding to this curve. So, namely, I'm going to write U for the inclusion of OC into OC of P1 plus P2. Sorry, I should have said, you know, it follows that 2P1 is twiddles the G12, twiddles 2P2. Right, because you know, if I calculate the canonical class of C, it is this plus this plus this, plus twice of this. Right, so canonical class of C is 2P1 plus 2P2 plus 2G12. However, the canonical class of C is also equal to 4 times G12. And the complete canonical system is equal to the complete 4G12. So this guy is something in there, and it's got a double point, and so it must be actually one of the G12s. Right. And so I'm going to write again, W is OC, includes into OC of P3 plus right, and then the ring of C and this P1 plus P2 plus G12 is equal to, so in degree 1 it's got x1 and x2. So, you know, maybe I need here's P1 with coordinates T1, T2. Right, so this is where the G12 lives. And let's arrange that P1 is given by T1 equals 0. And the other one, P2 is given by T2 equals 0. Right, so x1 is T1 times U, and x2 is T2 times U. Right, so I've got x1, x2 in degree 1, and what have I got in degree 2? So in degree 2, I'm supposed to have, this is Kc, so H0 of Kc is 5. And in that I've already got S2 of x1, x2. Right, so I've got x1 squared, x1, x2, x2 squared. So I need two more elements, y1 and y2. Right? But on the other hand, this Kc is 4 times the G12. Right? And so, you know, it's natural to take this y1. Maybe I need more clean. Okay, so in degree 1, I have the linear system, which is, you know, UT1, UT2. So this is P1 plus P2 as fixed points, plus the G12. Right, in degree 2, I have obviously the squares in these, and then I have T1 to the 4th, and then x1 squared, x1, x2, x2 squared, and T2 to the 4th. So you know, x1 has this 0 there, so he's not, so you know, this is T1 cubed, T2, T1 squared, T2 squared. Right. Maybe I put these back. Maybe this is y1 and y2 here. Okay, and so, you know, you can immediately write down the equations that these satisfy. These satisfy the equation y1 times x1 squared, x1, x2, and then x2 squared times y2. Right, and there's going to be a z1 and a z2 there as well. Okay, so in degree 3, what do we get? So, you know, the linear system is P1 plus P2 plus 5 times the G12. Right, this one is 4 times the G12. I'm just adding this and this. So what elements do we know in this? Well, we've got all the multiples of the guys that came from before. So, you know, if I have anything which is symmetric under the hyperelliptic involution, it's already a product of these guys. So the new guy comes from this W. And it turns out that I've got WT and WT1 and WT2. And so this one's called Z1 and Z2. Okay, so the divisor of W is P3 up to P12. What I'm saying here is that P3 plus P4 plus P12. And then, you know, if I added on P1 plus P2, this would be 6 times the G12. Right? This would be, you know, if I write the whole hyperelliptic curve as y squared equals F6, F12, then the divisor of y is all these zeros, right? And so this is so therefore this guy here is minus P1 plus P2, right? And that's this. Okay, so I've got a set of 6 equations here, which 2 of this equals 0. That's almost the same as before, right? And then I'm going to have 3 equations saying z1 squared, z1, z2, z2 squared equals. And you know, the problem here is that so there'll be, you know, t1 squared times something, t1, t2 times something, t2 squared times, you know, whatever it is that defines these 10 remaining points. Right, so I have to take these guys and rewrite them as cubics in x1, x2, y, y1, y2. Right? And you know, the problem is this is about as far as it goes. So we get a set of equations here, and you know, we don't really know the right way of rendering these equations. We know one way of rendering them, and then we can put them into deformation calculations. You can deform C in moduli space M, we're in genus 5. So that either point P1 or P2 moves in the half KC. Right, so let me draw a picture. Here's MG. Right, here's the hyperelliptic locus inside MG, which is much smaller. And then over the hyperelliptic equation, I have a choice of these two out of the 12 Weierstrass points. And then there's a kind of picture like this, which is that I can move out. So this is, remember, this is family 3, where the general curve has 2 of these base points. And here is family 2, so these ones where there was a single base point, and so it sort of looks like this. There's family 3, inside curves, family 3 is a line of double points of family 2. Right? In family 2 we have 1 base point, and so here this is just where the same curve suffers two of these accidents. It has 2 base points, right? And the 2 happen independently, right? So this is one result, and this is proved by writing down an equation of 9. By writing down a list of 9 equations of the right degree that generalize, that move these equations, depend on 2 parameters R and S, where R and S separately you know, control whether or not that point is a base point. And so, you know, it's just a calculation. We don't know how to make the calculation into some kind of reasonable, formatted expression. So to be, for example, a divisor in a determinantal variety, or one of these crazy, and you know, I don't know why it's difficult, but it is difficult. So this guy Duncan Dix did this, and he did it, you know, writing a 100-page thesis, and probably nobody's read it, including the examiners. Right. So taking the curve C out to a surface S still in family 2. This is easy. You just change the things here. So you can see the coincidences appearing in here. You know, if I move this one to be, you know, plus x naught or something, or plus x naught there, then I can so this can be done. This is unobstructed. This is this is practically unobstructed. Right. So now if I take you know, now I'm this is sort of more imaginary. Now I'm writing down the moduli space of surfaces with these invariants. Surfaces PG equals 3k squared equals 4. And I'm looking, so there's this part 3. Sorry, there's the part 2. The ones having a single base point, the ones I described earlier and said they're 5 by 5 Pfaffian. Right? And then there's family 3 here. And these don't meet, at least generically. We don't know if they intersect somewhere in the moduli space in surfaces. I mean, they probably intersect in the boundary of the moduli space. They don't intersect here. So this picture is very strange. So surfaces in family 3 deform to lose P1 and P2 from the base locus of Ks, but not independently. So you know, you've got a surface. It's got these two accidents. You do something to try to cure the accident there. So you have to change some of the coefficients in some of these equations, and you know, it turns out that if you do it at one point, then you have to do it at the other point as well. So you know, again, we don't understand why this is true. It's true as the final result of a very long calculation. And so, you know, this is not, you know, the world is not a perfect place, and the theory of algebraic surfaces has lots and lots of, you know, sticky corners and corners that are not well understood. So, you know, I have, you know, one of my problems in life is to eventually to try and understand this better, so that we can understand, you know, some kind of partial formats in which these results make sense. So there's a little, when I say practically unobstructed, there is a little obstruction at the bottom of this, and it's you know, there are two sets of deformation variables in degree -4 and in degree -2 and -4. And they multiply together into degree -6, and there is a singularity of the moduli space. So this part 3 place is actually a singularity of this moduli space. And you know, again, we know this is the result of calculations. We don't understand what it means. So it's possible, you know, so especially for graduate students looking for problems in the theory of algebraic surfaces, there are probably considerably easier places to look for problems than this. You know, there are. You know, I think some lady put out preprints about Horikawa surfaces on k squared equals 2pg and so on. I think these are harder than the ones she does. So I don't know. Anyway, when I come back next year, I will probably do sort of some lectures at least on more theoretical material in threefolds. So in the theory of threefolds. However, all of these ideas about canonical rings and how you write down generators and relations to them, they're really an important motivation to study threefolds. And we can, in some ways, I think it's probably true to say that in my career I moved from studying threefolds from studying surfaces to studying threefolds because surfaces were so hard. Okay, so thank you for listening to me.